Now we'll look at a few different types of radioactive decay. So I've put the important ones for us on the left-hand side, and I'll discuss what those are right now. So first type of decay is the decay in which a beta minus particle is produced. And what's happening here is the equation at the top of the right-hand side. So there's an excess of neutrons within the nucleus. So what the nucleus is going to do is it's going to take one of its neutrons, it's going to split it into a proton and a beta minus particle. And the mass is conserved because neutrons and protons have around the same mass. And the charge is conserved because +1 plus -1 becomes 0, which is equal to the left-hand side. And so what happens is the atomic mass stays the same because atomic mass is the sum of neutrons and protons. So as we see in the second equation, iodine with 131 is becoming xenon with an atomic mass of 131. So atomic mass is staying the same, but the element is changing because the atomic number is changing because there's a new proton in the nucleus now. And all the extra energy is put into this beta minus particle, which is thrown out of the the nucleus, which is what you can see in the diagram on the left-hand side. If the nucleus has excess energy after this beta minus decay has happened, it may also emit a gamma photon to get rid of that extra energy. And then the final product is the daughter nucleus, which is in the ground state. That is a state of lowest energy. So that's one type of decay. Another type of decay that we're looking at is isomeric transition. So isomeric transition is the transition between metastable states. And so let's just look at the graph, the figure on the left-hand side to understand what's happening here. So we have a radioactive parent, which is undergoing isobaric transition. That is the atomic number is changing, and then it's moving on to isomeric transition, which is so the first type of transition is between isotopes, and the second type is between isomers, which, as we've discussed, is where the atomic number and atomic mass of both the parent and the daughter are the same. But what is actually changing is the half-life and the radioactivity. And so the metastable state of an element has a different type of energy, and it has a high energy. And usually nuclei aren't able to stay in these states for very long, but there's some types of elements, very notably technetium, where the nuclide is able to stay in this excited state for a long time. And this is known as the metastable state. So let's take a look at what's happening here. If you look at the first equation on the right-hand side, it says AMXZ is moving to AXZ plus 00 gamma. So AMXZ means there's an element in the metastable state, and it's emitting a gamma ray, and it's moving to AXZ. That is the same element, but not in the metastable state anymore. So you can see the atomic number is exactly the same. The atomic mass is exactly the same. The only thing that's changing is the energy, and that energy is carried away by a gamma photon, which is the symbol on the right-hand side. And the famous example is molybdenum, which gets converted to technetium with the emission of beta minus and gamma. And then you have technetium in the metastable state. And technetium in the metastable state is going to emit a gamma photon and go to technetium not in the metastable state. I'm sorry, that equation should not have a plus gamma right at the end there. Okay, so we use isomeric transitions in imaging because the emission of the electron or the beta minus particle and the emission of the gamma photon happen at different times. So, and the reason we prefer it is because we don't want the electron emission to happen in the patient's body. The reason is that electrons contribute to the dose that the patient receives, but not the image which is being created. So we want gamma photons to be produced in a certain energy because that is going to create the image that we want, but the electron is just increasing the dose of the patient and not helping to increase the image. So this isomeric transition is an important transition and a useful one. Another type of emission is positron emission. So what's happening here is that in a neutron uh, deficit nucleus, the neutron is emitting a positron, and it's maintaining the same atomic mass, but it's um, decreasing its atomic number. Yeah. So, and it's the same thing as the other one. It may emit a gamma ray to reach the ground state. And the example given here is oxygen with an atomic mass of 15 and an atomic number of 8 is going to oxygen with an atomic number of 15 and 7. Nitrogen with an atomic mass of 15 and an atomic number of 7. And it's emitted that beta plus particle that we were talking about. Okay, the other type of decay that we're looking at is, so this is K electron capture. So again, we're looking at a nucleus which is neutron deficient. So what the nucleus is going to do to make a neutron is it's going to pull in one of the electrons from the nearest shell, which is the K shell. It's going to combine that with a proton, and it's going to form a neutron. So that's proton plus the K shell electron gives us a neutron. And so you can see what happens in the example on the top. So you have potassium. The potassium nucleus is capturing the nearest electron it can find. It's the proton and the electron are combining to form a neutron. So the atomic mass is staying the same. It's 40 on both sides, but the atomic number is decreasing because the nucleus has one proton less at this point. So it's become argon. So what happens when a vacancy is created in the K shell is that electrons from the other shells are going to fall into that vacancy to fill it. And when this happens, they're going to emit the K characteristic X-rays. Yeah, so that's this type of decay. And an example of this is, so what happens then is that you get both gamma radiation as well as this characteristic X-ray K shell radiation. And an example is iodine 123, which emits, I've just put this example here to give you an idea of what the numbers would look like. The K shell characteristic radiation won't be very energetic. So it emits 160 kilo electron volt gamma photon and 28 kilo electron volt X-ray photon, and no positive beta particles are emitted in this type of decay. Okay, so another type of decay process that we're going to talk about is internal conversion. So what happens in internal conversion is that the energy, which is usually carried away by the gamma photon, is actually absorbed by a nearby electron instead. And then what happens is that electron eats up that energy, which you usually lose as a gamma ray photon, and then it's ejected from its shell. And then an electron above will either fall into that vacancy or an auger electron will be produced. So basically a low energy characteristic X-ray will be produced. And what we have on the left-hand side is an image of all the different types of transitions which are occurring here. So if you have too many neutrons, we have the transitions which occur. If you have too few neutrons, you have or too many protons, you have the transitions which occur and all the different types of products which are created. So you can take a screenshot of this if you think it's helpful, but that's just a little summary of all the different types of decay. So just to run over it again, if you've got a good balance between the neutrons and the protons, then you have a stable nucleus. If you have too many protons, it'll undergo beta plus decay with the emission of a gamma photon. If you have too many neutrons, it'll undergo beta minus decay with the emission of a gamma ray. And if it's in an excited state, it'll go to the ground state in what is called isomeric transition by emitting a gamma ray. So really the way that we need to remember this is if there's too many protons, it needs to lose a proton. How does it do that? A proton and an electron are going to combine and form a neutron. And yeah, and vice versa, the other way if there's too many neutrons.